Hello everyone, I'm Dr. Bidyut Kumar Das, and today I'm going to discuss about atomic structure. So in this short video lecture, we'll be discussing about atomic structure, different models of atoms proposed by different scientists, then how to represent an atom, then the definitions of isotopes, isobars and isotones, and brief descriptions about the nucleus. So how does atoms look like? So atoms are so tiny or small that it's very difficult to observe them by naked eyes or by any scientific instruments. Therefore, based on the experimental evidences, the scientists proposed different models of atoms, and one of the famous models of atom was proposed by J.J. Thomson. So J.J. Thomson discovered the electrons in the late 19th century, and he proposed that atoms are just like a watermelon, and it is a positive. Atoms are in spherical shape, and the electrons and the positive ions are scattered throughout this spherical shell. This atomic model was highly appreciated at the time until Rutherford experiment was proposed. Now, to study the atomic structure of atom, Rutherford in the late 19th century did an experiment which is known as Rutherford alpha particle experiment. So this is the experimental setup of Rutherford's experiment. So Rutherford used a alpha particle source which is placed inside a box, and this box contains a small hole so that alpha particles, once it emitted from this source, so it will produce a beam of alpha particles. Now this is a gold foil, and the alpha particle beam is initially incident on this gold foil, and surrounding the gold foil this is a fluorescent screen. And initially Rutherford thought that since alpha particles are positively charged particles, and this is quite heavy particles compared to electrons, and we know that from Thomson's model of atoms are basically composed of electrons. So Rutherford's expectations was that alpha being a heavy particle, alpha particles doesn't have any effect with the interaction of the electrons, and it will passes through the gold foil in a straight line, and it will hit the fluorescent screen. So according to his expectations, so there will be no scattering of alpha particles once it passes through the gold foil. But when he did the experiment, Rutherford found that some of the alpha particles are highly scattered or highly deflected once it passes through this gold foil. Now, since the alpha particles are heavy particles and these are positive particles, and electrons being lighter particles, they cannot deflect alpha particle in such a large angle deviations. Therefore, Rutherford proposed that the atoms must have a positive core, and most of the masses of the atom concentrate on this positive core. And this positive core of the atom is basically responsible for the deflections of the alpha particles. And interestingly, in his experiment, Rutherford found that some of the alpha particles are deflected. Rather, you can say that these are reflected back from the gold foil at 180-degree angle. So from this experimental result, Rutherford proposed that the atoms are basically have a positive core at its center, and this positive core contains most of the mass of the atoms, and electrons are randomly scattered about this positive core. So after Rutherford's atomic model, Bohr in the beginning of the 20th century proposed a model of atom. So according to Bohr, in an atom, electrons are revolving around a positive core known as the nucleus. This nucleus is basically composed of protons and neutrons. And his second postulate, Bohr proposed that the electrons in a definite circular path has a definite energy. And for example, in a circular path, in any definite circular path, these electrons have a definite angular momentum, and this angular momentum is an integral multiple of h by 2h pi. So therefore these energy levels are known as quantized energy level. That means the electrons which is revolving around the nucleus in a circular path must have a definite angular momentum and energy. In the third postulate, Bohr proposed that if the electrons jump from the outermost energy level to a innermost energy level, then a photon will emit, and the photon, that is, which is equal to h nu, must be equal to the energy difference between these two energy levels, right? Similarly, if the atom gains some energy, for example, if you irradiate this atom by some high energetic photons, or if you heat the atom, and if the atom acquires energy which is equal to the energy difference between the two consecutive energy levels, then the electrons which is in the innermost energy level will jump into the outermost energy level by absorbing energy which is equal to h nu, and this h nu is equal to the energy difference between these two energy levels. Now, although the Bohr's atomic model is successful to describe lots of things in physics, but simultaneously it also produces lots of problem in defining some physical phenomena. So first, the Bohr's atomic model violates the Heisenberg uncertainty principle because it considers electrons to have both a known radius and orbit. So according to Heisenberg uncertainty principle, you cannot measure uncertainty principle, you cannot measure both the position and momentum simultaneously. That means if you measure position of a particle at a certain time, so at that moment you cannot measure the momentum of the particle. Or if you measure the momentum of the particle with 100% accuracy, then the error in calculating the position of the particle will be infinite. So in Bohr's atomic model, once you say that electrons are revolving around a certain circular path, that means you are basically saying that the electrons are revolving in a certain, but you are saying that you can measure the position of the electrons with 100% accuracy, which means that the momentum of the electron, or the error in calculating the momentum of the electrons will be infinite. So which is quite impossible. Now the second problem in Bohr's atomic model, that it provides an incorrect value for ground state of orbital angular momentum. And the third problem which arises in Bohr's atomic model, that it gives a very poor predictions regarding the spectra of large atoms. Simultaneously, Bohr's atomic model cannot predict the anomalous Siemens effect, or it cannot predict or explain the hyperfine structure of the spectral lines. So these are the few problems which a Bohr's atomic model cannot explain. Now from Bohr's atomic model, we have learned that electrons are revolving around the nucleus, and nucleus is basically composed of protons and neutrons. Now how to represent an atom? So atoms are basically represented by two parameters which is known as the mass number and atomic numbers. So mass number is represented by A, which is the total number of protons and neutrons. So these protons and neutrons altogether are called nucleons. Whereas the atomic number is the total number of protons in an atom. So always remember that in an atom, the number of protons and number of electrons are always equal, whereas the number of protons and the number of neutrons may not be equal. So we will be discuss these things in later slides. So atoms can be represented by this symbol, where A is the mass number and Z is the atomic number. So for example, you can see that this is sulfur. So the atomic number is 16, whereas the mass number is 14. For example, for chlorine, the mass number is 40, whereas the atomic number is 17. Now let us consider this argon atom, which is mass number is 40 and atomic number is 18. So from this mass number and atomic number, we can easily find out what is the number of neutrons present in the argon atom. So in this case, the number of neutrons can be found out by subtracting the atomic number from the mass number, which is equal to 22 in this case. Now let's talk about how to measure atomic mass, or what is the atomic mass. So we know that atom is composed of protons, neutrons and electrons, and each of these particles have a definite mass. So if we add all these masses together, so it should be the mass of the atom. So practically this is true, but unfortunately if you add proton, neutron and electron masses together, so the atomic mass always less than the total mass of these particles because of the binding energy. Binding energy means binding energy means since protons, neutrons and electrons are attracted each other by different forces, therefore the total mass of the atom is always less than the total mass of the individual particles if we add together. On the other hand, atoms are so tiny or so small that conventional units of masses, for example kilogram or gram, it's not appropriate to represent the atomic masses. For example, if you see, the mass of the electron is 9.1095 into 10 to the power minus 31 kg, whereas the mass of the proton is 1.6726 10 to the power minus 27 kg, which are very small mass in terms of kilogram. Therefore, a new unit is basically used to measure the atomic mass, which is known as the atomic mass unit, and it is represented by U. So what is the atomic mass unit? So it is basically the 1/12 of the mass of carbon-12 atoms. That means it is basically 1/12 mass of the one carbon-12 atoms. Now let's calculate 1 U, or 1 atomic mass unit, in terms of kg. So we know that 1 mole of carbon-12 atom consists of so we know that 1 mole of carbon-12 atom is equal to 12 into 10 to the minus 3 kg, and again 1 mole contains 6 into 6.62 10 into 10 to the power 23 numbers of carbon-12 atoms, which is the Avogadro's number. Therefore the mass of one atom will be equal to this mass, right? So therefore 1 atomic mass unit will be equal to 1.6605 10 to the power minus 27 kg. Now if we represent the mass of the electron, proton and neutrons in terms of atomic mass units, so we will find that the mass of the electron in terms of atomic mass unit is equal to 5.4858 into 10 to the power minus 4 U, whereas the mass of the proton is approximately equal to 1.007 atomic mass unit, and the mass of the neutron is equal to 1.0086 atomic mass unit, or U. So we can say that the mass of the neutron is little bit greater than the mass of the proton, whereas the mass of the electron is much smaller compared to the proton and the neutrons. So let's talk about the nucleus of an atom. So we have already learned that the nucleus is composed of protons and neutrons, and protons are basically positively charged particles, whereas neutrons are neutral particles. But these protons and neutrons are held together inside a nucleus by a very strong short-range force, which is known as the nuclear force. So nuclear force is basically a short-range force. That means, unlike Coulomb force, which is a long-range force, this nuclear force is very attractive when the particles remain very close to each other. One thing you must know that most of the atoms having lower atomic numbers, the number of protons and number of neutrons are always equal. So these are the most stable atoms, and as the atomic number increases, so since we know that the protons are positively charged particles, so these protons repels each other, and to minimize this repulsion between the protons, so the number of neutrons also increases for higher atomic mass number atoms. So from this graph you can see that as you increase the atomic number, then in order to minimize the repulsion, that is Coulomb repulsion between the protons, the number of neutron also increases, and this increase of neutrons inside a nucleus is basically due to the stability of the atoms. That means for higher atomic number atoms, if the number of protons and number of neutrons remain equal, then those atoms are not stable. They will be very unstable atoms, and so to make them stable, the number of neutrons must have to be increased. And this is the band of stability, and the straight line shows the equal number of protons and equal number of neutrons, and the stability of the atoms deviates when the atomic number increases. So you should also remember that unstable atoms always emit some particles like alpha, beta or gamma particles in order to be a stable atom. Now let's talk about isotopes, isobars and isotones. So isotopes are atoms which have different number of mass numbers, and they have the same atomic numbers. For example, the uranium-235 and uranium-239 are basically two isotopes of uranium. So here you see the atomic mass of uranium 235 and 239 isotopes have the same atomic number, which is equal to 92. On the other hand, isobars have the same mass number, but they have different atomic number. For example, sulfur, chlorine, argon, calcium, potassium, these all elements have the same mass number, that is 40, but they have different atomic numbers. On the other hand, isotones have the same numbers of neutrons, but they have different mass numbers. For example, the sulfur, chlorine, argon, potassium, then calcium, These are called the isotones because they have the same numbers of neutrons, which is equal to 20.